The universe is a place of almost unimaginable scale, a silent, sprawling ocean of darkness, dotted with islands of unimaginable light and energy. For all of our history, humanity has looked up into that darkness and asked the same fundamental question: are we alone? For decades, the primary way we sought an answer was by listening, tuning our most sensitive instruments to the cosmos, hoping to catch a stray whisper in the dark, a deliberate message sent from another intelligence. But this is like searching for a single voice in a cosmic ocean, an endeavor that depends entirely on someone else choosing to speak at the exact right moment, in the exact right direction. It's a question that connects us all, no matter where on this planet we are. I'd love to know where you're listening from and what time it is for you, so please leave a comment. And if you enjoy these journeys into the cosmos, be sure to subscribe so you're notified of future stories. Because a profound shift in thinking has begun to take hold, a new approach to the search that is both simple and breathtakingly ambitious. What if, instead of listening for whispers, we started looking for monuments? What if the greatest evidence of intelligent life isn't a message, but a shadow, the unmistakable footprint of a civilization so advanced its sheer existence alters the appearance of its solar system? At the heart of this new search is a simple, undeniable truth. All life, and especially technological life, needs energy. And as a civilization grows, its energy demands would eventually become so vast that they would outstrip anything its home planet could provide. The ultimate source of power in any solar system is its star, and a truly advanced species would inevitably turn to that star, seeking to harness not just a fraction of its energy, but all of it. This logical endpoint leads us to one of the most audacious and spectacular ideas in the history of scientific thought: the hypothetical megastructure known as the Dyson sphere. It is a concept that exists at the very edge of imagination, a thought experiment that attempts to visualize the ultimate expression of technological power. This is the story of that idea, not just as a piece of engineering, but as a revolutionary new tool in the search for extraterrestrial intelligence, a concept that transformed our hunt for aliens from a passive listening exercise into an active search for the calling cards of the gods. But the seeds of such god-like engineering were not first planted in the sterile soil of scientific journals. Like so many of our grandest ideas about the future, the concept first bloomed in the fertile fields of human imagination, specifically in the mind of a man who was less a scientist and more a dreamer of cosmic epics. His name was William Olaf Stapledon, a British philosopher and author born in the late 19th century, a man whose life spanned the tumult of 2 world wars and whose mind reached out across billions of years of cosmic time. Stapledon was not your typical writer of scientific romances. While his contemporaries were often content with tales of rocket ships and adventures on Mars, Stapledon's vision was immeasurably vaster. He was a philosopher first, preoccupied with the grand sweep of evolution, not just of a single species on a single planet, but of life and consciousness itself, across entire galaxies and throughout the whole lifespan of the universe. In 1937, as the world teetered on the brink of another global conflict, he published his masterwork, a novel titled Star Maker. It is a book that defies easy categorization. It is less a story with characters and plot, and more a breathtaking metaphysical journey. The narrator, an unnamed Englishman, finds his consciousness projected out of his body and across the cosmos, where he becomes a disembodied observer, a wandering viewpoint drifting through space and time, witnessing the rise and fall of countless alien civilizations on countless worlds. It is within this grand cosmic tapestry that Stapledon first laid the conceptual groundwork for the Dyson sphere. As the narrator of Star Maker travels, he observes that many intelligent species, upon reaching a certain stage of technological and philosophical maturity, inevitably face the same ultimate problem: the finite lifespan of their star. They come to understand that their sun, the very source of their life and energy, is also a ticking clock, destined to one day swell into a destructive giant or fade into a cold, dark cinder. For these ancient, wise civilizations, the solution was as logical as it was ambitious. They began to build. Stapledon described how these species would deconstruct their sister planets, mining entire worlds for raw materials, and use them to construct a vast, delicate sphere of artificial worlds and energy collectors around their parent star. He described it as a gossamer sphere of light traps, a vast, intricate network of orbiting habitats, all flying in precise formation. A celestial string of pearls designed to intercept every single photon of light, every joule of energy that their star produced. This was not a crude, brutalist shell, but an elegant and living structure. The inner surfaces of these myriad worlds would be turned into new homes, engineered paradises, bathed in the perpetual, perfectly managed light of their captured sun. From the outside, a passerby would see only a dim, infrared glow, the faint waste heat leaking from a civilization that had turned its star into a private power station and a celestial hearth. Stapledon's vision was profound because he provided not just the what, but the why. The civilizations in Star Maker did not build their stellar enclosures purely for industrial power. It was a spiritual and existential imperative. They sought to create a perfect symbiosis with their star, to become a single, integrated system of life and energy. Within these spheres, consciousness could flourish, unburdened by the precariousness of planetary life. The minds of the inhabitants could merge, forming collective intelligences, planetary brains, that could contemplate the deepest mysteries of existence for trillions of years, long after their original home world was a forgotten memory. They did this to survive the death of their star, to carefully shepherd its energy, nursing it through its final phases, and using its last flickers of light to propel their consciousness onward to new stars and new galaxies when the old one finally died. He imagined that as a galaxy aged, it would become filled with these dark spheres, each one a silent, glowing monument to a civilization that had achieved a kind of practical immortality. A traveler passing through such a mature galaxy would see not a brilliant river of stars, but a collection of faint, ruddy embers in the dark, each one concealing a vibrant, thriving inner world of unimaginable complexity. The sheer scale of this idea was, for 1937, almost incomprehensible. The science of cosmology was still in its infancy. The concept of nuclear fusion as the engine of the stars was only just being worked out. The idea of alien life was largely confined to bug-eyed monsters. Yet here was a philosopher calmly outlining a multi-trillion-year survival plan for an entire species. Stapledon was writing about a Type II civilization in the language of a scale that would not even be invented for another 3 decades. His work was deeply influential, a quiet undercurrent in the river of science fiction that would shape the generations to come. Authors like Arthur C. Clarke and Brian Aldiss would openly credit Stapledon as a major inspiration. His vision of cosmic engineering and the vast, almost geological timescales on which intelligent life might operate raised the bar for what science fiction could be. He demonstrated that the genre could be a powerful tool for philosophical inquiry, a way of asking the biggest questions we can ask about our place in the universe. While his books may not have reached a mass audience in the same way as his more action-oriented peers, his ideas seeped into the collective consciousness of the scientific and engineering communities. He planted a seed, the idea that the signature of a truly advanced intelligence might not be a radio signal, but the visible act of cosmic renovation, the deliberate rearrangement of a solar system for the purposes of life. The idea lay dormant in the world of fiction for over 20 years, a spectacular piece of imagination waiting for a mind that could bridge the gap between speculative fantasy and theoretical physics. Someone who could take this incredible vision of a star in a bottle and place it on a firm scientific footing. That mind would belong to a brilliant and unconventional young physicist named Freeman Dyson, who would independently arrive at a strikingly similar conclusion, and in doing so, give the concept a name and a new scientific life that would propel it from the pages of a dusty novel into the heart of the modern search for extraterrestrial intelligence. The man who would give this cosmic vision its name and its scientific substance was born into a world of quiet intellectualism and impending change. Freeman, John Dyson entered the world in 1923 in the village of Crowthorne in Berkshire, England, the son of a composer and a lawyer. From his earliest days, it was clear that his was a mind of unusual power. He was a true prodigy in mathematics, a boy who saw the world through the elegant and intricate language of numbers, reportedly trying to calculate the number of atoms in the sun when he was still a small child. Yet Dyson was never destined to be a narrow specialist, a thinker confined to the rigid tramlines of a single discipline. He was an intellectual omnivore, possessed of a boundless and restless curiosity that would eventually lead him far beyond the tidy certainties of pure mathematics. His formative years were overshadowed by the looming specter of the Second World War, and upon coming of age, he did not serve as a soldier on the battlefield. Instead, his war was fought in the quiet, methodical world of operational research for the Royal Air Force's Bomber Command. There, the brilliant young mathematician was confronted with the brutal, statistical reality of life and death. His job was to analyze the efficiency of bombing raids, to calculate probabilities of survival, and to find ways to minimize the catastrophic losses of air crews. It was a grim and sobering education. He saw firsthand how elegant theories could shatter against the hard, messy realities of engineering and human factors. He learned that the most important questions were not always the most mathematically beautiful ones, and he developed a deep and abiding respect for the practical, a skepticism of pure abstraction that would inform his work for the rest of his life. After the war, Dyson's prodigious talent carried him to the heart of the revolution that was shaking the world of physics. He emigrated to the United States in 1947, drawn to Cornell University to study under the masters who were then deciphering the strange new rules of the subatomic world. This was the heroic age of modern physics, an era of unprecedented confidence and discovery. The atom had been split, its immense power unleashed, and it seemed as though there were no problem, no matter how vast, that humanity could not solve with the tools of science and reason. Dyson found himself in the company of giants like Hans Bethe, who had unlocked the secrets of the stars, and the brilliant, eccentric Richard Feynman. It was here that Dyson made his first great mark on science. At the time, physicists were struggling to understand the interaction of light and matter, a field known as quantum electrodynamics. There were two competing theories, one by Julian Schwinger and one by Richard Feynman, that both seemed to work but looked wildly different and were mathematically irreconcilable. During a long cross-country bus journey, the young Dyson, with his unique ability to see the underlying unity in disparate ideas, managed to prove that the two theories were, in fact, just two different ways of saying the same thing. His paper, published in 1949, unified the field and provided one of the cornerstones of modern physics, a theory so precise its predictions have been confirmed to an astonishing degree of accuracy. This achievement cemented Dyson's reputation as a physicist of the first rank. But his mind was already moving on. He soon settled at the Institute for Advanced Study in Princeton, New Jersey, the same revered institution where Albert Einstein had spent his final decades. Freed from the pressures of teaching, Dyson's curiosity was allowed to roam freely across the entire landscape of science and technology. His interests began to drift towards the future, towards the grand challenges that humanity would one day face. He became deeply involved with Project Orion, a top-secret and breathtakingly audacious plan to build a spacecraft propelled by a series of controlled nuclear explosions. The idea was to construct a ship the size of an office building, weighing thousands of tons, that would be lifted into space on a continuous wave of atomic detonations. The physics was sound, and for a time, it was considered a serious proposal for deep space travel, a way to reach Mars and Saturn by the 1970s. Project Orion, though it was ultimately shelved, was crucial in shaping Dyson's thinking. It accustomed him to contemplating engineering on a planetary, even solar, scale. It trained his mind to think in terms of colossal energy budgets and the marshalling of vast resources. He was already thinking about how a civilization might practically move through its solar system and manipulate its environment. It was in this intellectual climate, a heady mixture of Cold War ambition, atomic age confidence, and the dawn of the space race, that Dyson turned his attention to the search for extraterrestrial life. In 1959, physicists Giuseppe Cocconi and Philip Morrison had published a landmark paper suggesting that if aliens were trying to contact us, they would likely use a specific radio frequency, the 21 centimeter or 1,420 megahertz hydrogen line, a universal and unmistakable cosmic marker. This paper effectively launched the modern search for extraterrestrial intelligence, or SETI, and the dominant paradigm became one of listening, of tuning our radio telescopes to the heavens in the hope of eavesdropping on a conversation between the stars. Dyson, however, approached the problem from a different angle, one informed by his background in practical, large-scale systems. He began not by asking how aliens might choose to communicate, but by asking a far more fundamental question. What are the unavoidable necessities of any advanced technological civilization? His answer was simple: energy. He performed a straightforward calculation, extrapolating humanity's own growing energy consumption into the future. He assumed a modest, steady growth rate of 1% per year. The result was staggering. Within a few thousand years, a mere blip in cosmic time, the energy demands of our civilization would become so great that we would require the entire energy output of the sun to sustain them. This wasn't a matter of choice. It was, he argued, an inevitable consequence of technological expansion. From this, he made the crucial logical leap. If this trajectory was inevitable for us, it would be equally inevitable for any other technological species. They, too, would eventually be forced to graduate from the limited resources of their home planet to the immense, untapped power of their parent star. They would have to build a structure to capture it. He envisioned a society disassembling its outer planets, perhaps a world like Jupiter, and using the raw material to construct a vast swarm of orbiting collectors and habitats that would completely enclose their star. In June of 1960, Freeman Dyson published his thoughts in a brief, one-page paper in the prestigious journal Science. Its title was unassuming: Search for Artificial Stellar Sources of Infrared Radiation. In it, he laid out his simple, powerful logic. Don't listen for a whisper. Look for a shadow, for the unavoidable waste heat, the telltale infrared glow of a star that has been enclosed by a civilization of cosmic engineers. He had independently arrived at the same grand vision as Olaf Stapledon, but he had stripped it of its philosophical poetry and recast it in the clear, sharp language of physics, transforming a piece of literary imagination into a concrete, testable scientific hypothesis. With this new scientific footing, the concept of a star-encompassing megastructure burst from the realm of speculative fiction into the arena of serious, theoretical possibility. Yet the name itself, the Dyson sphere, conjures a powerful and intuitive image, one that has become deeply embedded in the popular imagination, but is, in fact, profoundly misleading. We tend to picture a single, solid object, a colossal, metallic shell encasing a star, like a gargantuan piece of celestial armor. It is an image of ultimate power and control, seen countless times in science fiction, most famously as the planet-destroying battle stations of cinematic space operas. This vision of a rigid, monolithic sphere is simple, dramatic, and almost certainly impossible. Freeman Dyson himself never envisioned such a structure, for he, like any physicist, understood that a solid shell would be a monument not to engineering genius, but to catastrophic failure. The problems are twofold, and they are fundamental. The first is a matter of celestial mechanics, a deadly gravitational trap. A hollow sphere does not exert a net gravitational pull on anything inside it. A star placed at the perfect center of such a shell would simply float there. But the universe is not a perfect place. The slightest perturbation, the gravitational tug of a passing star, the impact of a large comet, or even the uneven pressure of the star's own solar wind, would cause the star to begin drifting off-center. Once it moved even a tiny distance, the gravitational pull of the closer side of the shell would become stronger than the pull from the farther side. This imbalance would create a runaway effect, pulling the star ever faster towards the inner wall, culminating in a cataclysmic collision that would obliterate both the star and the trillions of inhabitants of the structure. It would be like trying to balance a pin on its point, an inherently unstable equilibrium that the slightest breath of wind would doom to collapse. An advanced civilization would not build a celestial tomb for itself. The second problem is one of sheer physical strength. Let us imagine a sphere built at the same distance from its star as the Earth is from our Sun, a radius of roughly 150 million kilometers, or 93 million miles. The forces involved in holding such an object together are beyond staggering. If the sphere were to rotate to simulate gravity on its inner surface, the tensile strength required to prevent it from tearing itself apart would exceed that of any known, or even theoretically conceivable material. Diamond would shred like wet paper. Graphene would shatter. Even the hypothetical strong nuclear force material of a neutron star would be insufficient. The sphere would have to be built from something we can't even imagine, a material held together by pure, wishful thinking. A non-rotating shell would be no better, as it would be under immense compressional stress from its own gravity, and would be prone to buckling and catastrophic collapse. The dream of a solid, unified world enclosing a star is a fantasy of materials, science, a blueprint that ignores the fundamental laws of physics. Dyson's own conception, the one he outlined in his paper, was something far more subtle, more organic, and ultimately more plausible. He did not envision a shell, but a swarm. Imagine not a single solid object, but a loose, thick cloud of trillions of independent objects, each one in its own stable orbit around the star, like a flock of birds or a swarm of bees on a cosmic scale. This collection of objects could be anything: solar energy collectors, industrial platforms, space habitats, entire artificial worlds. Each component would be an individual satellite, following Kepler's laws of motion, gravitationally stable and independent of all the others. The swarm would not be built in a day. It would be the end result of a long, gradual process of industrial expansion. A civilization would begin by building a few orbital habitats and power stations, perhaps in a ring like our own asteroid belt. Over the centuries and millennia, they would continue to add to it, constructing more and more objects, filling in the gaps. They would likely mine the raw materials from their system's outer planets and asteroids, disassembling entire worlds to fuel their ever-growing celestial city. As the number of orbiting components grew, they would begin to intercept more and more of their star's light. Eventually, after thousands or even millions of years of continuous construction, the swarm would become so dense that it would effectively block almost all of the visible light from the star, catching its energy for the civilization's use. This swarm concept elegantly solves the problems of the rigid shell. There is no gravitational instability, because each component is in its own stable orbit. There are no impossible material requirements, as each habitat or collector would only need to be strong enough to support itself. It is a modular, scalable, and resilient design. A collision between two components would be a localized disaster, not a civilization-ending cataclysm. This vision also opens up a far richer and more diverse possibility for what life inside might be like. It would not be a single, uniform inner surface, but a near infinite variety of worlds. Some habitats might be spinning cylinders, creating Earth-like gravity, vast nature preserves filled with genetically engineered forests. Others might be zero-gravity laboratories or crystalline palaces for beings who had long since abandoned their physical forms. The Dyson swarm is not a single place, but a meta-structure, a solar system transformed into a single, sprawling, interconnected city of worlds, with a population numbering not in the billions, but perhaps in the trillions or quadrillions, all powered by the captured light of their star. While the swarm remains the most scientifically robust model, other variations on the theme have been proposed. One of the most intriguing is the Dyson bubble. This concept relies not on orbital mechanics, but on radiation pressure. The idea is to build a vast number of extremely large, incredibly lightweight satellites called statites, essentially enormous solar sails. These would not be in orbit at all. Instead, they would be pushed outward by the constant stream of photons and charged particles from the star, the solar wind. Their position would be maintained by balancing this outward pressure against the star's inward gravitational pull. A complete Dyson bubble would be a stationary shell of these statites, hovering in place, floating on a cushion of starlight. Another famous variant, popularized in fiction by the author Larry Niven, is the ring world. This is a solid, spinning ribbon, 1,000,000 miles wide and encircling its star, a compromise between the impossible sphere and the diffuse swarm. While still requiring materials of incredible strength, it avoids the gravitational instability of a full sphere. These variations all underscore a central point. The exact architecture of a Dyson structure could take many forms, tailored to the specific needs and technological capabilities of the civilization that built it. But whether it is a swarm, a bubble, a ring, or some other design beyond our imagining, the ultimate consequence for an outside observer remains the same. A star that was once a brilliant point of visible light would be transformed. Its light would be captured, used, and inevitably degraded into waste heat, re-radiated away into space at a much lower temperature in the invisible spectrum of infrared light. The construction of a Dyson sphere is the ultimate act of stellar renovation. And like any major construction project, it leaves a clear and unmistakable signature for anyone looking in the right way. This fundamental shift in perspective transformed the search for extraterrestrial intelligence from a hopeful game of chance into a targeted exercise in forensic astronomy. The genius of Freeman Dyson's proposal lay in its reliance not on alien psychology, but on alien physics. The search for a radio message is, at its core, a guess about sociology. It assumes another species would be talkative, that they would choose to broadcast their existence using a technology we could recognize, and that they would do so in our direction at a time we happen to be listening. It is a search for a deliberate, communicative act. Dyson's method, however, requires no such assumptions. It is a search for an unavoidable consequence. It rests on one of the most unshakable pillars of physics, the second law of thermodynamics. This law, in its essence, states that no process is 100% efficient. Whenever energy is used to perform work, whether it's a star fusing hydrogen, a tree growing leaves, a computer processing data, or an alien civilization powering its cities, some of that energy is inevitably lost as waste heat. It is the universe's ultimate tax, and there are no loopholes. A civilization building a Dyson sphere would be the greatest energy consumer in its solar system. They would be capturing the colossal energy output of their star, perhaps trillions upon trillions of watts, and using it to power their society. But no matter how advanced their technology, the second law dictates that they cannot make all of that energy simply disappear. It must be radiated away. And because they would likely want their habitats and systems to operate at a temperature conducive to life or complex machinery, this waste heat would be radiated at a much lower temperature than the star itself. A star like our Sun has a surface temperature of thousands of degrees Celsius, peaking in the visible spectrum of light. The waste heat from a Dyson sphere, however, might be radiated at a comfortable room temperature, perhaps around 300 Kelvin, which is about 27 degrees Celsius, or a comfortable 80 degrees Fahrenheit. An object at this temperature does not glow visibly. It glows in the infrared part of the spectrum. To a distant observer with the right kind of eyes, the star would vanish. In its place in the sky would be a new and deeply strange object, a point source that is completely dark in visible light, yet shines brightly as a colossal beacon of infrared radiation. It would be a ghost star, its presence betrayed only by its warmth. This insight provided astronomers with a completely new and powerful search strategy. Instead of pointing radio telescopes at sun-like stars and listening, they could now use infrared telescopes to scan the entire sky, looking for these anomalous heat signatures. The search became less about finding a needle in a haystack and more about looking for a haystack that was inexplicably warm. The first dedicated infrared sky survey was carried out by the Infrared Astronomical Satellite, or IRAS, launched in 1983. A joint project between the United States, the Netherlands, and the United Kingdom, IRAS orbited the Earth for 10 months, methodically mapping 96% of the sky in the infrared. For the first time, we had a comprehensive catalog of the universe's heat sources. Scientists combed through this vast new dataset, a treasure trove of hundreds of thousands of objects, searching for the telltale signature of a Dyson sphere. The task was far from simple. The universe is full of things that are cool and glow in the infrared. Giant clouds of interstellar dust, the nurseries where new stars are born, can look very similar. So can old, dying stars that have shed their outer layers, creating a shroud of warm dust around themselves. The challenge for astronomers was to become cosmic detectives, to learn how to distinguish the signature of a natural dust cloud from the artificial heat signature of a colossal engineering project. They developed a set of criteria to filter the suspects. They looked for objects that were perfect black bodies, meaning they radiated heat smoothly across the infrared spectrum, which might be more indicative of a solid, engineered object than a clumpy, irregular dust cloud. They focused on objects with a temperature profile consistent with a life-supporting structure, not the frigid cold of deep space dust or the scorching heat of a protostellar disk. Despite these efforts, the IRAS data and subsequent surveys yielded no definitive smoking gun candidates. The sky, it seemed, was not filled with these obvious and complete stellar enclosures. But this lack of discovery did not end the search. It simply refined it. Scientists realized that finding a fully completed Dyson sphere, one that captures 100% of its star's light, might be unlikely. Such a project would take millennia, if not millions of years, to complete. It was far more probable that if we were to find anything, we would find a civilization in the process of building one. A partially completed Dyson sphere would present a different, more subtle, and perhaps even more tantalizing signature. The star would not vanish from the visible spectrum. It would still shine brightly, but its light would be accompanied by a significant and anomalous excess of infrared radiation, the heat signature from the sections of the swarm already in place. It would look like a normal star wearing a warm, invisible cloak. Furthermore, the light from this star might behave strangely. As massive, non-luminous sections of the swarm, perhaps continent-sized engineering projects or newly constructed habitats, passed between the star and our telescopes, they would block some of its light. This would cause the star's brightness to dip in ways that could not be explained by a natural orbiting planet. The dips would be irregular, aperiodic, and could vary dramatically in depth, betraying the presence of a vast, complex, and artificially structured cloud of objects. This new understanding, the search for a flickering star with a strange fever, set the stage for one of the most exciting and perplexing astronomical mysteries of the 21st century. The hunt for Dyson spheres had evolved. It was no longer a search for the silent, glowing embers of ancient, completed empires, but a search for the flicker and hum of a construction site, the active, ongoing process of a civilization reaching for the sublime. and in doing so, creating a cosmic light show that just might be visible from 100,000 trillion kilometers, or nearly 62,000 trillion miles, away. The search for such a monumental construction project did more than just provide a new target for telescopes. It fundamentally reframed the entire question of what we are looking for. Dyson's idea implicitly suggested that civilizations might evolve along a predictable path of energy acquisition, graduating from the limited resources of a planet to the boundless power of a star. This notion of a cosmic energy ladder, a way to measure a civilization not by its philosophy or its biology, but by its power consumption, was formally crystallized just a few years later by a brilliant Soviet astrophysicist working on the other side of the Iron Curtain. His name was Nikolai Kardashev, and in 1964, he gave the universe a new yardstick, a way to classify hypothetical alien societies that would forever link his name to the grandest scales of cosmic engineering. Nikolai Kardashev was a product of the intense scientific and ideological fervor of the Soviet Union during the Cold War. A radio astronomer by training and a protege of the great Iosif Shklovsky, he was deeply immersed in the nascent field of the search for extraterrestrial intelligence. The space race was at its zenith, and for both the Soviets and the Americans, the discovery of life beyond Earth was seen not just as a scientific prize, but as a potential ideological victory. In this heady atmosphere, Kardashev was examining the problem from a uniquely practical perspective. As a radio astronomer, he was interested in the power required for a civilization to transmit a detectable signal across interstellar distances. He quickly realized that the ability to send such a message was inextricably linked to the total amount of energy a civilization had at its disposal. This line of inquiry led him to propose a simple, elegant, and profoundly powerful classification system. A scale not of technological sophistication in the abstract, but of raw, measurable power. He presented his idea at a conference in Burikan, Armenia, laying out a three-tiered system for the evolution of intelligent life. The first step on this cosmic ladder he called a Type 1 civilization. This is a society that has achieved complete mastery over the energy resources of its home planet. A Type 1 civilization would be able to harness the total amount of stellar energy that falls on its world, an amount roughly equivalent to 10 to the power of 16 watts. This is a level of power that is still a distant dream for us. Humanity, for all our technological progress, currently operates at around 10 to the power of 13 watts. The visionary physicist Carl Sagan later refined this scale, suggesting a more granular approach, where he estimated modern humanity to be a civilization of about Type 0.7, a true type. One society would be a true master of its globe. It could control the weather, prevent earthquakes, and mine its planetary core. It might build a worldwide energy grid powered by fusion reactors, drawing fuel from the oceans, or vast solar collectors in orbit that blanket the planet in clean, limitless energy. A Type 1 civilization is a planetary power. Its influence and its engineering projects confined to its own world and its immediate orbital neighborhood. The next step, however, represents a leap in scale so vast it is difficult to fully comprehend. A Type 2 civilization, according to Kardashev, is one that has exhausted the potential of its home planet and has moved on to harness the entire energy output of its parent star. To do this, it would need to consume roughly 10 to the power of 26 watts, a 10 billion-fold increase in power over a Type 1 society. This is the stage where the Dyson sphere transitions from a theoretical possibility to an engineering necessity. A Type 2 civilization would be the architects of their solar system, capable of moving planets, igniting gas giants, and constructing artificial worlds. Their home would no longer be a single planet, but the entire solar system itself, all of it powered by the star at its center, now functioning as a perfectly regulated engine. The construction of a Dyson sphere or swarm is the defining characteristic, the final exam, for a civilization graduating to Type 2 status. From our distant vantage point, their home star would dim and cool, its visible light being siphoned off for use, its presence betrayed only by the enormous, ghostly bloom of its waste heat in the infrared spectrum. The final category in Kardashev's original scheme is a Type 3 civilization. And here we leave the realm of stellar engineering and enter the domain of the truly godlike. A Type 3 society would have outgrown even the power of a single star and would have learned to harness the energy of its entire host galaxy. We are now talking about the coordinated output of hundreds of billions of stars, a power consumption on the order of 10 to the power of 36 watts. It is difficult to even speculate about the technologies of such a civilization. Perhaps they would build Dyson spheres around every suitable star in their galaxy, creating a vast, interconnected power grid spanning 100,000 light years, or roughly 950,000 trillion kilometers. Perhaps they would have learned how to feed matter directly into the supermassive black hole at the galactic core, turning the most destructive object in the universe into their own personal power plant. A Type 3 civilization would be so advanced that its activities would be visible across intergalactic distances. It might appear to other astronomers as a dark galaxy, one that shines brightly in the infrared but has mysteriously vanished in visible light. Some have even proposed that the strange, hyperluminous objects known as quasars could be the industrial signatures of Type 3 civilizations at work. The Kardashev scale, though speculative, provided an invaluable theoretical framework for the search for extraterrestrial intelligence. It gave astronomers a concrete set of observable targets. If you are looking for a Type 1 civilization, you might search for planets with atmospheres showing signs of industrial pollutants or unnatural heat distribution. If you are looking for a Type 2, you scan the heavens for the infrared signature of a Dyson sphere. And if you are looking for a Type 3, you examine entire galaxies for anomalous energy profiles. The scale transformed the search from a passive listening exercise into an active hunt for the physical evidence of cosmic engineering. It firmly established the Dyson sphere not just as a piece of imaginative fiction, but as the most plausible and sought-after sign of a civilization taking the most significant step up the ladder of cosmic evolution. It was only a matter of time before astronomers found a star that seemed to fit the description, a star that flickered and dimmed so erratically that it would ignite a firestorm of scientific debate and, for a brief, exhilarating moment, raise the incredible possibility that we had finally stumbled upon the colossal handiwork of an advanced alien civilization. The stage for this extraordinary astronomical drama was set not in a fabled, ivy-covered observatory of old, but in the vast, democratic river of data flowing from a new kind of telescope. For centuries, the practice of astronomy had been a patient, solitary vigil, an observer sitting at an eyepiece, meticulously sketching a nebula or timing the transit of a planet. But the dawn of the 21st century brought a new paradigm: the automated sky survey. NASA's Kepler Space Telescope, launched in 2009, was a prime example of this revolution. Its mission was not to study a few specific stars in exquisite detail, but to stare, unblinking, at a single vast patch of the sky in the constellation Cygnus, continuously monitoring the brightness of more than 150,000 stars simultaneously. Its primary goal was to find exoplanets, which it did by looking for the tiny, regular dips in a star's light caused by a planet passing in front of it. The torrent of data Kepler produced was far too massive for professional astronomers to analyze alone. So, in a groundbreaking move, the Kepler team enlisted the public, launching a citizen science project called Planet Hunters. They uploaded the light curves, graphs of star brightness over time, to the internet, and invited anyone with a curious mind to help search for the telltale dimming of a potential new world. It was within this digital cosmos, in 2011, that a group of these volunteer astronomers noticed something utterly bizarre. They were looking at the light curve of a star designated KIC 846285, a fairly ordinary F-type star, slightly larger and hotter than our Sun, located about 1,470 light-years away, or nearly 14,000 trillion kilometers away. The star's light curve was unlike anything anyone had ever seen. The dip in its brightness were not the small, brief, and perfectly periodic dimmings of an orbiting planet, which typically block less than 1% of a star's light. These were colossal, plunging drops in brightness, lasting for days or even weeks. And they were wildly irregular. One event caused the star's light to dim by an astonishing 15%. Another, even more dramatic event saw its brightness drop by a staggering 22%. To put this in perspective, for a planet to cause a 22% dip in this star's light, it would have to be a gas giant 1,000 times larger than Jupiter. A physical impossibility. This was not a planet. This was something else entirely. The professional astronomers were, at first, skeptical. They suspected instrumental errors or data artifacts. But after years of careful reanalysis, they confirmed that the signal was real. The star was indeed behaving in a profoundly strange way. The lead author of the paper that would eventually announce the discovery was an astronomer at Yale University named Tabitha Boyajian. And so, the celestial enigma was affectionately nicknamed Tabby's star. Boyajian and her team meticulously worked through every conceivable natural explanation they could think of. Perhaps the star was surrounded by a massive, clumpy disk of dust and debris, a kind of supersized asteroid belt. But such disks are usually found around young stars, and Tabby's star was a mature, middle-aged star. Furthermore, a cloud of dust that dense should be glowing brightly with its own heat in the infrared spectrum. Yet observations showed no such excess infrared radiation, a fact that seemed to defy the laws of thermodynamics. Maybe the dimming was caused by a vast swarm of comets, a great celestial traffic jam. A collision in the star's distant Oort cloud could have sent a massive wave of comets plunging inwards, their dusty tails temporarily obscuring the star. This became the leading natural hypothesis. But it too had problems. The sheer number of comets required to produce the observed dimming was almost unthinkably large, and it was hard to see how such a swarm could sustain itself over the multiple years the dimming events were observed. With all the conventional explanations proving inadequate, the scientific community began to whisper about a far more exotic, far more exciting possibility. In October of 2015, Tabitha Boyajian and her co-authors published their paper, and in it, they included a brief, cautious mention of the fact that the strange light curve was consistent with the passage of a swarm of megastructures. The idea was further amplified by Jason Wright, an astronomer from Penn State University, who had been actively searching for the signatures of Dyson spheres. He pointed out that while the object didn't have the massive infrared glow of a completed sphere, its erratic, deep dimming was precisely what one might expect from a vast, partially built Dyson swarm under construction. The dips in light could be caused by enormous, irregularly shaped structures, solar collectors the size of continents, unfinished habitats, or industrial platforms, all moving in a complex, non-periodic orbit as they were being assembled. The media seized upon this extraordinary possibility. Headlines around the world blared with the news that astronomers might have found an alien megastructure. For a brief, intoxicating moment, it felt as though humanity was on the verge of the most profound discovery in its history. The SETI Institute turned its powerful radio telescope arrays toward the star, listening intently for any artificial signals, any radio chatter from the putative alien engineers. The results were silence. But as Dyson had argued decades earlier, the absence of a radio signal proves nothing. A civilization advanced enough to re-engineer its solar system might have moved beyond radio communication, or simply might not feel the need to broadcast to its primitive cosmic neighbors. The scientific community, energized by the mystery, threw every instrument it had at the star, telescopes across the globe and in orbit, monitored its every flicker. The public, captivated by the story, crowdfunded a dedicated observational campaign, allowing astronomers to book telescope time to ensure the star was never out of sight. As more data poured in, the mystery only deepened. Researchers looking at historical photographic plates from the past century discovered that, in addition to its short-term, erratic dimming, the star also seemed to be fading slowly and steadily over the course of decades, losing nearly 20% of its overall brightness in 100 years. A rate of change that is utterly unprecedented for a stable star of its type. For several years, Tabby's star remained the greatest mystery in astronomy, a genuine anomaly that defied all easy explanation. It became a powerful symbol of Dyson's idea, a real-world test case for the search for cosmic engineering. While the alien megastructure hypothesis was always considered an extreme long shot, a possibility of last resort, the fact that it was being seriously discussed by mainstream scientists represented a sea change in the field of SETI. It showed that the search for intelligence had matured beyond just listening for signals and was now actively hunting for the physical footprints of technology on a cosmic scale. Eventually, a more plausible, albeit less thrilling, natural explanation began to gain traction. Further observations in multiple wavelengths of light revealed that different colors of starlight were being blocked by different amounts. Dust blocks blue light more effectively than red light, and this is precisely what was observed. This suggested that whatever was obscuring the star was not made of large, solid, opaque objects, as an alien megastructure would be, but of a fine, translucent cloud of microscopic dust particles. The leading theory now suggests that we may be seeing the aftermath of a colossal planetary or cometary collision, or perhaps a planet-eating star that has consumed one of its own worlds, leaving a vast and complex cloud of debris in its wake. While the mystery is not yet definitively solved, the alien megastructure hypothesis has faded, but the legacy of Tabby's star endures. It was a fire alarm in the night, a tantalizing glimpse of a signal so strange it forced us to consider the most profound possibilities, and it proved that the universe is still capable of showing us things that are far beyond our immediate understanding. Even as the strange case of Tabby's star recedes from the headlines, settling into the more prosaic realm of natural cosmic phenomena, the grand vision it temporarily embodied, the Dyson sphere, continues to cast a long and powerful shadow over both science and the human imagination. The sheer audacity of the concept forces us to confront the ultimate limits of engineering and the almost terrifying scale of resources required to turn a solar system into a personal habitation. Contemplating the construction of a Dyson sphere is an exercise in thinking on a level that dwarfs every human endeavor to date. It is a blueprint for infinity, a project whose material and energy requirements are not just large, but literally astronomical. The first and most obvious challenge is the raw material. Where would a civilization find enough matter to build a structure that surrounds an entire star? The answer, as both Stapleton and Dyson intuited, lies in the rest of the solar system. The rocky inner planets are far too small. Even if we were to dismantle Mercury, Venus, Mars, and every asteroid and moon in our system, we would still fall woefully short of the mass needed for a substantial swarm. The true prize, the great cosmic quarry, would be the gas giants. Jupiter, in our own solar system, contains more than twice the mass of all the other planets combined. A civilization embarking on this grand project would need to become masters of star lifting and planetary disassembly, developing technologies capable of siphoning off the hydrogen and helium from a gas giant's atmosphere, and more importantly, mining its dense, rocky core. This process, sometimes called planet lifting, would itself be an engineering project of almost unimaginable scale, requiring energy on a planetary level just to get started. It would be a bootstrap problem of cosmic proportions. You need to capture a star's energy to mine a planet, but you need to mine a planet to build the structures to capture the star's energy. Presumably, the process would be gradual, with the first solar collectors and habitats built from more accessible asteroid material, powering a growing industrial base that would eventually become powerful enough to tackle the giants in the outer solar system. The logistics of such an operation are mind-boggling. Automated, self-replicating robotic factories, perhaps von Neumann probes on a colossal scale, would be needed to process this planetary material, refining it into structural components, solar collectors, and habitat modules. These finished parts would then need to be transported and assembled in a precise, ever-growing orbital pattern around the central star. The construction would not be a single project, but a continuous, multi-generational process, a slow and steady conversion of a chaotic solar system of tumbling rocks and gas balls into a perfectly ordered, life-sustaining machine. The final structure would be the largest and most complex object that it is physically possible to build, a monument not to a king or a nation, but to the collective will and technological prowess of an entire species over countless millennia. The finished swarm would be a triumph of celestial mechanics, a cosmic clockwork of trillions of independent pieces all moving in perfect harmony. While the engineering challenges are formidable, it is in the realm of science fiction that the Dyson sphere has truly flourished, becoming a powerful and enduring icon of technological ambition. Long before it became a serious target for astronomers, it was a staple of the literary and visual imagination, a go-to concept for any storyteller wishing to evoke a sense of truly cosmic scale and power. One of the most famous and influential depictions appeared in the iconic television series Star Trek: The Next Generation. In the 1992 episode Relics, the crew of the Starship Enterprise discovers a massive, abandoned Dyson sphere, a solid shell 200 million kilometers, or 125 million miles, in diameter. The awe-inspiring visual of their tiny starship against the colossal, curving inner surface of a sun-encircling world, its interior landmass larger than billions of Earths, seared the concept into the minds of a generation. Although the episode depicted the scientifically problematic solid shell variant, it perfectly captured the sense of wonder and the almost archaeological feel of discovering the relic of a civilization so far beyond our own. The Dyson sphere has become a recurring motif in almost every corner of speculative fiction. In the world of literature, authors like Larry Niven with his Ring World, a 1.6 million kilometer or 1 million mile wide ribbon around a star, and Alistair Reynolds with his vast star-enclosing orbital rings, have explored the societal and personal implications of living in such artificial worlds. These stories delve into the unique cultures that might arise in a civilization that has conquered scarcity and mortality, where the very concepts of day and night are engineered constructs. Video games, too, have enthusiastically embraced the concept. Games like Stellaris or EVE Online allow players to build and manage their own galactic empires, with the construction of a Dyson sphere often representing the ultimate technological achievement, the endgame of a civilization's journey. In these interactive worlds, the sphere is not just a backdrop, but a strategic asset, a source of near limitless power that can fuel fleets of warships or sustain utopian societies. This constant presence in popular culture has created a powerful feedback loop. Science fiction has familiarized the public with the idea, making it less alien and more conceivable, which in turn fuels scientific interest and the public support for projects that search for such artifacts. The line between the imagined blueprint and the real-world search blurs, with each feeding the other's sense of possibility. Ultimately, the Dyson sphere's greatest legacy may not be as a physical object, but as a thought experiment. It serves as a kind of cosmic Rorschach test, a mirror reflecting our own aspirations and anxieties about the deep future. It forces us to ask fundamental questions about the ultimate goals of civilization. Is relentless expansion and energy consumption the inevitable destiny of any intelligent species? Or is it a sign of a kind of technological immaturity, a brute force approach to survival that a more enlightened, more efficient society would transcend? The sphere represents a fork in the road of cosmic evolution. One path leads to a future where biology and technology merge to conquer the physical limitations of their environment on the grandest scale possible. The other path might lead inward, towards mastering the inner space of consciousness, or transitioning to a purely digital existence where energy needs are minimal. The Dyson sphere is the ultimate symbol of the first path. It is a declaration, written in the language of physics across an entire solar system, that a civilization chose to remain in the physical universe and to master it completely, bending the very light of its parent star to the service of life. It is a monument to the idea that the ultimate destiny of intelligence is not just to understand the universe, but to rebuild it. This monument to possibility, then, has traced a remarkable arc through the landscape of human thought. It began as a whisper in the philosophical fiction of the 1930s, a grand, metaphysical vision of cosmic survival from the mind of Olaf Stapledon. It was then reborn 2 decades later, independently conceived and forged into a testable scientific hypothesis in a single transformative page of a physics journal by Freeman Dyson. From there, it became the celestial yardstick for a Type II civilization on Nikolai Kardashev's grand scale of cosmic evolution, giving astronomers a concrete, physical artifact to hunt for. The search for its ghostly ember, the faint infrared echo of a captured star, fundamentally altered the search for extraterrestrial intelligence, turning our gaze from the ear to the eye, from listening for whispers to looking for shadows. The strange and baffling case of Tabby's star, for all its eventual grounding in natural phenomena, gave us a tantalizing, real-world glimpse of what such a discovery might feel like, igniting a global conversation and proving that the idea of cosmic engineering had firmly taken root. From the blueprints of our most imaginative fiction to the rigorous data of our most advanced telescopes, the Dyson sphere has served as the ultimate symbol of technological ascent. Whether one is ever found, its true value may lie not in its physical existence, but in its power as a concept. It is a story we tell ourselves about the future, a cosmic blueprint that challenges the limits of our ambition. It forces us to contemplate timescales that dwarf human history and engineering projects that would demand the deconstruction of worlds. The search for Dyson spheres is, in the end, a search for our own reflection in the cosmic mirror, a quest to find evidence that survival and growth on a truly astronomical scale are not just a fantasy. It is a story that encourages us to look up at our own sun, not just as a source of light and warmth, but as a reservoir of untapped potential, a silent promise of the futures that we, too, might one day be capable of building.